to we're going to look at some dynamics, and then we'll get into momentum, angular momentum. So how do we deal with forces? When we were dealing with forces and we had force equals mass times acceleration, we called that dynamics because we now had an equation and some kind of a law that we could follow and work things out with forces in straight lines. Now, if we're rotating things, how do we do that? It turns out that we can't just talk about mass when we rotate things, because it doesn't matter. The mass matters when you rotate things, but it also kind of depends where the mass is. And let me give you a good example of this. Hopefully I can give you a good example of this. Let's take, for example, not only does it matter where the mass is, but it matters where the force is. So location of things matters. First, let's talk about the location of a force, because I think that's the easier one. If you have a door that you're trying to open, and let me see if I can go to a place to draw really quick. Let's go to Educreations and take a look here. Okay. So let's apparently that's not my email address. Oh yeah. I must not have had the right password. Let's try this one. Well, I don't know what my password is then. There it is. Okay. So let's go ahead and create a new lesson here really quick. Excuse me. Sorry. So let's say that we are trying to open a door. So here's our hinge of our door, and our door sticks out this way. Normally we put the doorknob over here, and we push at the door knob to open the door right here, and we can use a pretty small force. But anybody who's tried to open a door for someone else and maybe has tried to push not so close to the doorknob, maybe right here, you know that your force has to be huge. It has to be monstrous. Whereas this force could be pretty small. And that's because distance plays a role in torque. If you have a bigger distance, you get a bigger torque for a smaller force, or for the same force. So if you increase that distance, your force can be smaller. It's the same with wrenches. If you want to really tighten a nut or really loosen a nut, you need a long handle on your wrench, and so on and so forth. And so the placement of the force matters. Where the force acts is important. But also where the mass is can be important as well. For example, if you have a merry-go-round and we look at it from the top, and here's our merry-go-round, it's got the little handles on it that stick out like this, you know. And you put a little kid on the outside, put a whole bunch of little kids out here, right? I'm only going to draw one, but let's pretend there's 20. And then you try to rotate this thing, try to push it this way, you're going to have to push with a huge amount of force. However, if that kid is right in the middle, it's a small amount of force that you have to push with. It requires much less force if you put them in the middle. And this can be seen in lots of different situations. Maybe the merry-go-round isn't the best one because not many people have done that, I guess. But a lot of different situations illustrate this point. For example, tires on cars have steel belts in them, and the bigger the tire, the more steel belts they have. So racing wheels on race cars have a tendency to be a big rim with just a tiny little tire on the outside. The reason for this, there's a couple of reasons, but one of the reasons for this is that if you have a smaller tire, you have less steel in the tire. And less steel means less weight on this outer edge, just like having less kids on the outer edge of the merry-go-round. If it's less kids on the outer edge, it takes less force. You can have a smaller force acting on this wheel to get it going. Okay? And people say, well, what about the rim? Because the rim is big, but the rim is made of aluminum, and it turns out to be a lot lighter than the steel in the tire. So you don't want a lot of steel outside there on the tire. And this is one reason why big trucks with big tires cannot accelerate like small cars or smaller trucks with smaller tires. Those big, the huge tires that are 3 or 4 feet across or whatever, and they've got a lot of tire on them. The hub in the middle is just this tiny little thing. It's a big old tire with big old knobs on it or whatever. All this weight out here, a lot of it is steel, and rubber's not light either. But you have all this steel in this tire way out on the edge, and you cannot accelerate that thing around. Can't get it going around fast. It matters where the mass is, and the distance matters. So it's a big deal. We can actually see this when we talk about torque. Excuse me. Because torque is equal to the mass times the distance times the sine of the angle, right? Well, the mass times the distance is there. Not the mass times the force. The force times the distance. So here's our force times our distance here, right? Well, if our force is directly proportional to the mass and where the mass is or where the force is, the r, the distance, then we actually get up an equation that looks like this: m times r times alpha. And this also comes from just replacing acceleration with r times alpha from our rotational kinematics. So we get force equals m times r times alpha, right? Well, if we multiply both sides by r, we get r times f, which is starting to look like torque, equals m times r squared times alpha. And then we get torque equals mr squared alpha. And this equation right here is actually really interesting because it looks a lot like force equals mass times acceleration. It's torque equals mass times r squared times angular acceleration, but it's almost like a mass times acceleration. So what we do is we take this stuff that's in front of the angular acceleration, and we call it something else besides mass, because it's not just mass, it's mass times distance squared. So we call this actually the rotational inertia. And then we can rewrite this equation so it looks like Newton's second law. We can write it as torque, or the net torque, total torque, equals rotational inertia, or sometimes called just inertia or angular inertia or whatever, or moment of inertia is what they're calling it here, moment of inertia. So the net torque equals moment of inertia times angular acceleration, which looks a lot like net force equals mass times acceleration. We just replaced mass with I, and we're using angular acceleration instead of linear acceleration. That's fine. But once we do that, we realize that we can use all the same laws that we used before. We can use Newton's second law, and we can use the kinematics equations with rotation and everything else. But we do need to know how to use that I in different situations, because that one situation was just a mass some distance away from a rotational angle. But what if you have different shapes? What if the mass is spread out over different shapes like this? Well, they've actually calculated them for us. If the mass is spread out into a ring around your rotational axis, which is the green axis, then you use a moment of inertia of m times r squared. If it's a disk, a cylinder rather, that has some thickness to it, so there's two radii, an inside and an outside radius, then use this equation to calculate that moment of inertia. And you can do it for all kinds of different shapes and different ways that it's going to rotate. And they show you all these different ones here. In this next problem, we're going to calculate the effect of mass distribution on a merry-go-round. What happens if you put the kids in different places or things in different places? So right now, this guy is just turning the merry-go-round. The merry-go-round is kind of like a big flat disc, and we actually know what the moment of inertia is for a big flat disc. It's, well, right here. So a solid cylinder or a disc, it's the same one, about the center axis through the disc, so it's rotating around its center axis, ends up having a moment of inertia of the mass of the disc times the radius squared divided by 2. So we just use that. We can actually calculate from the net torque equals I times alpha. We can calculate alpha to be equal to torque over I. And if we know what I is, which we can calculate, then we can be done with this problem. And we can also, if we can also calculate the torque. So we figure out the torque from RF sine theta. And then we use the moment of inertia from the previous page, 1/2 mr squared. We plug them in this equation and we calculate their angular acceleration. Turns out the angular acceleration in this particular case will be 6.67 radians per second squared. And once we've calculated that alpha, then we're essentially done with part A because that's what they want. In part B, they want to change. We want to change because we're going to put a child on the merry-go-round. Now we're going to have a kid on there. When you have a kid on there, it's like adding a mass, except instead of adding a mass, we're going to add some moment of inertia. So we're going to calculate the moment of inertia of the child, and we're going to add that to the moment of inertia for the merry-go-round. So moment of inertia for child is just like a mass on the end of a string or something, so it's just mr squared. Throw that in there. Here's your moment of inertia, 28.13 kilogram meter squared. Then we're going to add that to the 56.25 kilogram meter squared that we calculated up here for the merry-go-round. And it just works. If you just add those two moments of inertia together, you get 84.38, and then you plug them into alpha equals torque over inertia, moment of inertia. Plug that 84.38 in for your moment of inertia. Use the torque that you calculated earlier up here, right here. And then you can divide the two, and you get 4.44 radians per second squared for the angular acceleration. So you can see that with the kid off of there at 6.67 radians per second squared, which means it speeds up faster in rotating. And then this one rotates slower as you try to speed it up with the same amount of force. And you would expect that. You put some mass on there, it's harder to turn the thing. But that's not the only thing we can do. I mean, we can also do kinetic energy. It turns out that the kinetic energy equation, we just replace mass with the moment of inertia again for whatever object it is. And we can replace just about everything in everywhere. And so rotational kinetic energy just ends up being 1/2 I times omega squared. So instead of mass, it's I. Instead of velocity, it's omega squared. And this is rotational speed times 1/2 times the moment of inertia of the object. So you need to know the moment of inertia, or you need to be able to calculate it. In this example, we're going to calculate a person who is going to slow down a grindstone by putting their hand on the grindstone and kind of exerting some pressure on it without killing themselves, mangling their hand. They tell us that she's going to exert a force of 200 newtons, and that 200 newtons is going to be exerted through a rotation of 1 radian, and that the force is kept perpendicular to the grindstone. Okay, so anyway, the kinetic energy rotational is 1/2 I omega squared, just like linear is 1/2 mv squared. So the I takes the place of the m, the omega takes the place of the v, so it's rotational velocity now. And then we know that in the end, the net work will equal the net torque that is done. Right? So we go ahead and start calculating some things. So net work, which is going to be R times F times theta, because that's the net force, applied force, multiplied by the radius, and then we've got a angle theta there for how much angle it goes through. And then you're multiplying by 0.320 meters, the 200 newtons, and the 1 radius given in the problem. And you get your answer. Let's see here. They give so they want us to find. They also want us to find the final angular velocity. Well, you're just going to use kinematic equations. That's all they're doing here. It's just kinematic equations. They're also using those to with the net force or the net torque equals RF. They're also using it down there, but this is kinematic equations for the most part. And then down here in part C, it's the rotational kinetic energy. Again, so not too much difficult stuff here. Done it before, we just did it with linear stuff. Yeah, here they have some races of different things. And then, of course, we want to combine kinetic energy, rolling or rotating kinetic energy with linear kinetic energy. And so you actually just put it into the equation. Our conservation of energy equation before had potential energy initial plus kinetic energy initial equals potential energy final, kinetic energy final. Well, you have to now split your kinetic energy into translational or linear and rotational. We have 2 times of kinetic energy, just like we have 2 times of potential energy. We had gravitational and spring, but now we have 2 types of rotational kinetic energy as well. Not really that big a deal. So then we move on to angular momentum, because angular momentum is also conserved. And I'm going to save that for another video so I can take some time with it. I need to take a little break right now. So I'm going to go ahead and end this video and save it, and I'll get back to you for the last one.